November 16, 1942. The Columbia River churns dark and cold beneath a slate-grey sky as 20,000 workers crowd the banks of Kaiser's Vancouver shipyard in Washington state. They're not here for another Liberty ship launch. Those happen almost daily now, routine spectacles that barely merit local newspaper coverage anymore. They're here because their colleagues inside the yard are attempting something the Navy said was physically impossible: a complete warship, from bare steel plates to launch-ready hull, in less than 72 hours. Inside the yard, Superintendent Clay Bedford checks his stopwatch for the 100th time in the past hour. 71 hours, 40 minutes since they laid the keel. Around him, if you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The prefabricated sections of a small landing craft sit in perfect sequence, each piece numbered and mapped, waiting for the final welds that will transform scattered metal into a functioning vessel. Each component was built in separate factories across the country, shipped by rail to Vancouver, through a logistics network that rivaled military operations and staged in precise order for assembly. Traditional shipbuilders called it madness. Ships weren't manufactured like automobiles. They were crafted, piece by piece, by skilled artisans who understood the subtle stresses and flexing of a hull at sea. The Navy Bureau of Ships called it reckless. Welded construction was still suspect. Prefabrication eliminated quality control. Kaiser's methods sacrificed durability for speed. Henry Kaiser called it the future. Bedford doesn't care what they call it. He cares about one thing. In 20 minutes, this vessel will slide into the Columbia River, proving that American industry can build warships faster than Germany can sink them. The mathematics are brutal and undeniable. In 1942, German U-boats are sending Allied ships to the bottom at a rate that makes victory mathematically impossible. Every week, more tonnage disappears beneath the Atlantic than all the world's shipyards combined can replace using traditional methods. But if Kaiser's system works, if prefabrication and welding can truly replace centuries of shipbuilding tradition, America might build its way to victory, one modular section at a time. The workers know the stakes. Many of them weren't welders 6 months ago. They were waitresses and farmers and shopkeepers, housewives and mechanics and draftsmen, trained in Kaiser's crash programs that turned complete novices into productive workers in 2 weeks. The established shipbuilding unions had protested. You couldn't learn proper welding in 2 weeks. It took years of apprenticeship, careful mentorship under master craftsmen, gradual advancement through journeyman status. Kaiser's rapid training was producing inferior workers who'd compromise structural integrity. Now those supposedly inferior workers are executing the most audacious manufacturing challenge in naval history. They're welding faster, cleaner, and more consistently than many journeymen with years of experience. And the entire Pacific War may depend on whether they can pull it off. This is not a story about one welder, despite what the title suggests. This is a story about a man who had never built a ship in his life, who looked at centuries of naval tradition and saw inefficiency waiting to be eliminated. A man who believed that the same principles that built dams could build destroyers. A man whose methods were so revolutionary that the established shipbuilding industry spent years insisting they couldn't possibly work, even as his yards launched vessels at speeds that rewrote every assumption about what was achievable. His name was Henry John Kaiser, and in 1942 he was about to prove that sometimes the most dangerous person in a crisis is an outsider who doesn't know what's supposed to be impossible. The path to that 72-hour launch began not in present, a shipyard, but in the desert. In 1931, Henry Kaiser stood at the edge of Black Canyon on the Colorado River and saw something nobody else could see. Not the towering canyon walls or the powerful river or the impossible challenge of damming one of North America's most formidable waterways. He saw a mathematical problem about moving material faster than it had ever been moved before. Kaiser was 50 years old and had spent 3 decades building roads, highways, and civic projects across the American West. He'd made his fortune doing things the established construction industry said were impossible, mostly by ignoring how things had always been done and asking a simpler, more fundamental question. How do you move the most material in the least time with the fewest workers? The answer wasn't better tools or stronger workers. The answer was better workflow. Eliminate waiting, remove bottlenecks, optimize every movement, make every action purposeful, and most importantly, never accept that something must be done a certain way simply because it's always been done that way. The Hoover Dam project would become his masterpiece of efficiency innovation. Traditional construction methods called for building forms on site, pouring concrete in place, and waiting for it to cure before moving to the next section. This sequential approach meant massive crews standing idle while concrete hardened. Kaiser's team prefabricated massive forms off-site, transported them by specially designed railroads, and orchestrated a continuous pour that kept concrete flowing 24 hours a day. Instead of sequential steps with idle periods, Kaiser created parallel workflows where every crew was productive simultaneously. They invented truck-mounted drilling jumbos that could drill dozens of holes simultaneously, replacing teams of men with hand drills who could only work one hole at a time. They designed custom railroads specifically for moving aggregate from quarries 8 miles away, optimizing the gradient and routing to minimize travel time. They installed refrigeration systems to cool concrete pours, preventing heat cracking and allowing faster placement cycles. Most importantly, Kaiser fostered competition among his crews. He split his work teams and rewarded the fastest with bonuses and public recognition. On the Grand Coulee Dam project, 2 Kaiser teams raced to complete their halves of the spillway first. The rivalry drove both teams to innovations in workflow and technique that cut months off projected timelines. Workers who'd been content with good enough performance suddenly pushed for excellence because their peers were watching and competing. By 1939, Kaiser and his consortium, the 6 companies, had completed the Hoover Dam 2 years ahead of schedule. They'd finished the Bonneville Dam and the Grand Coulee Dam, massive hydroelectric projects that powered the industrial development of the Pacific Northwest. They'd built the San Francisco-Oakland Bay Bridge, connecting 2 major cities with engineering that pushed every boundary. They'd pioneered the use of arc welding in large-scale construction, replacing traditional riveting in pipelines and structural work with faster, lighter, more reliable welded joints. Kaiser had become known as a man who could move mountains of earth and rivers of concrete faster than anyone thought possible. His methods were studied at engineering schools. His projects came in under budget and ahead of schedule. He was the man you called when conventional approaches wouldn't work. He had never built a ship. That changed in the fall of 1940, when the world was at war and Britain was drowning under a tide of submarine attacks. The Battle of the Atlantic was going catastrophically wrong for the Allies. German U-boats were sinking merchant ships faster than British and American yards could replace them. In September 1940 alone, U-boats sank over 400,000 tons of Allied shipping. In October, 380,000 tons. In November, 430,000 tons. The mathematics were stark and terrifying. Britain needed food, oil, and munitions from America to survive. Those supplies crossed the Atlantic in merchant ships. German submarines were sinking those ships at an unsustainable rate that, if continued, would starve Britain into surrender by mid-1942. British shipbuilders, following centuries of tradition refined through generations of practice, needed 6 to 8 months to build a single merchant vessel. They built from the keel up, one crew of specialized shipwrights working piece by piece, riveting steel plates together in a process that had barely changed since the late 19th century. It was craftsmanship, not manufacturing. Each ship was essentially custom-built, fitted and adjusted by experienced tradesmen who understood how hulls flexed and stressed. It produced excellent ships, but produced them slowly. A British delegation arrived in America in the fall of 1940 with a desperate proposal. Could American shipyards build 60 merchant vessels to replace catastrophic losses? The request went to established East Coast shipbuilders, who assured Washington they could handle it using traditional proven methods. They could deliver quality ships in 6 to 9 months per vessel. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. perhaps faster if they hired additional crews. Henry Kaiser, monitoring the situation from his California offices, did the mathematics that nobody in Washington seemed willing to calculate honestly. At 6 months per ship, those 60 vessels would take 5 years to complete if built sequentially, or require massive expansion of existing yards if built in parallel. German U-boats weren't waiting years. They were sinking ships today, tomorrow, next week, next month. Even if every existing American yard operated at full capacity using traditional methods, Allied shipping losses would exceed in production for at least 2 years. Kaiser saw the same problem he'd seen in the desert at Hoover Dam. This wasn't about building better ships. It was about building more ships faster than the enemy could sink them. It was fundamentally a production problem, not an engineering problem. And production problems could be solved with workflow optimization and parallel processing. He called his partner the Todd Shipbuilding Company and proposed something audacious. They would bid on a contract to build 30 of the British ships, splitting production between Todd's East Coast facilities and a brand new yard Kaiser would build in Richmond, California. Kaiser would apply mass production techniques to shipbuilding, extensive prefabrication, assembly line methods borrowed from automotive manufacturing, and most controversially, comprehensive welding instead of traditional riveting. The established shipbuilding industry was horrified. Kaiser had never built a ship, never studied naval architecture, never supervised a marine construction project. He knew nothing about the specific stresses ships encountered at sea, the corrosive effects of salt water, the flexing and working of hulls in waves. His proposals violated centuries of accumulated wisdom about how ships were properly constructed. Welding was suspect. Prefabrication sacrificed quality for speed. His methods would produce inferior vessels that would break apart in rough seas or fail at critical moments. Todd, Kaiser's partner, initially welcomed the contract but quickly became uncomfortable with Kaiser's revolutionary methods as they saw the details. By 1941, Todd had effectively withdrawn from the partnership, leaving Kaiser to pursue his vision alone. He'd promised to deliver ships using methods the industry insisted would fail catastrophically, to specifications he'd never worked with. In a new yard he was building from scratch on a mudflat in Richmond, California, with a workforce that didn't yet exist. The Richmond site was literally a mudflat when Kaiser arrived. Within 4 months, his crews transformed it into one of the largest shipyards in America. While traditional yards built ships on sloped ramps called ways, Kaiser designed his facility around modular prefabrication. Separate buildings would manufacture standardized sections, bulkheads, deck plates, engine mounts, and superstructures. These modules would be transported to assembly areas where they'd be welded together in predetermined sequences like assembling a 3-dimensional puzzle. The design was based on a British tramp steamer called the Ocean Wind, a workhorse cargo vessel designed for economical operation rather than speed or elegance. The naval architecture firm Gibbs & Cox modified it for American production, simplifying some elements and adjusting specifications for materials available in the United States. The specifications called for a 441-foot cargo vessel powered by an outdated, triple-expansion reciprocating steam engine, the same basic technology used on ships at the turn of the century. Modern steam turbines weren't available. Every turbine produced in America was allocated to warships, destroyers, cruisers, battleships, and carriers. So the emergency cargo ships would use decades-old reciprocating engine technology that was inefficient but simple, reliable, and manufacturable, without competing for scarce turbine production capacity. The Navy and Maritime Commission didn't care about elegance or advanced technology. They cared about carrying capacity and construction speed. Each ship needed to carry 9,000 tons of cargo in 5 holds, with additional capacity on deck for vehicles, aircraft, or ammunition. They needed to be simple enough that hastily trained merchant marine crews could operate them, and basic enough that emergency repairs could be made at any port worldwide with minimal specialized equipment. President Franklin Roosevelt, personally, attended the launching of the first 14 ships on September 27, 1941, less than 3 months before Pearl Harbor would bring America into the war. He named the program the Liberty Fleet Day and christened the first vessel the Patrick Henry, after the Revolutionary War patriot who declared, "Give me liberty or give me death." The name Liberty Ship stuck immediately, despite Roosevelt's private opinion to intimates that they were dreadful-looking objects compared to sleek pre-war cargo vessels. They were indeed ugly. Newspaper reporters called them ugly ducklings. Naval architects winced at their blunt, utilitarian lines. Maritime Commission Chairman Rear Admiral Emery S. Land joked that one was a real ugly duckling, though he meant it affectionately, recognizing that beauty was irrelevant compared to cargo capacity. But Kaiser didn't care about aesthetics or what maritime traditionalists thought. He cared about tonnage delivered per day of construction time. And that's where his revolution began to show dramatic results. The first Liberty ship built at Kaiser's Richmond Yard, the Ocean Vanguard, took 197 days from keel laying to delivery. Traditional shipbuilders smirked knowingly. That was actually slower than some conventional yards working with established methods. Kaiser's revolutionary techniques weren't revolutionary at all. They were just different, and not obviously better. Perhaps the industry veterans had been right all along about the superiority of proven traditional approaches. But Kaiser and his team were learning with every ship. Every vessel revealed inefficiencies in the workflow. Every delay identified a bottleneck that could be eliminated. Every worker's complaint or suggestion highlighted an opportunity for improvement. Kaiser sent his right-hand man, Clay Bedford, to study Ford's assembly line techniques at an automobile manufacturing plant in Michigan. Bedford returned with ideas about workflow optimization, standardization of parts, strategic positioning of workstations, and the systematic use of welding that would transform the Richmond Yard's operations. The key insight was the comprehensive application of welding. Traditional shipbuilding used riveting exclusively. Steel plates overlapped at joints and were secured by driving red-hot rivets through pre-drilled aligned holes. Each rivet had to be heated to cherry red temperature, thrown from the heating forge to a catcher, positioned in the hole, and hammered flat by a driver using a pneumatic hammer. It required immense skill developed over years. A journeyman riveter needed 6 months of intensive training and practice. Riveting teams consisted of 4 specialists working in precise coordination. A heater to heat the rivets, a catcher to receive and position thrown rivets, a holder-on to brace the rivet from the opposite side, and a driver to hammer it into place. It was loud enough to cause permanent hearing damage, labor-intensive, requiring 4 skilled workers per team, and relatively slow compared to welding. Welding, by contrast, could join steel plates edge to edge without overlap, saving substantial material. A typical Liberty ship required 3,500 tons of steel. Eliminating rivet overlap reduced that by approximately 10%, saving over 300 tons per ship. Multiplied across thousands of ships, that material savings alone justified the switch. Welding was faster. 1 skilled welder could execute joints that required a 4-person riveting team. It was quieter, eliminating the deafening hammer impacts that plagued traditional yards. And most importantly for Kaiser's purposes, welding could be learned much more quickly than riveting. Kaiser's training programs took complete novices, people who'd never held a welding torch or even seen welding performed, and made them productive in as little as 2 weeks for the simplest repetitive tasks. This was revolutionary, because it solved Kaiser's fundamental labor problem. The shipyard needed thousands of workers immediately. Traditional riveting crews took 6 months to train properly. That timeline was unacceptable. Welding allowed Kaiser to hire anyone willing to learn and put them to work in weeks instead of months, dramatically expanding the available labor pool. But welding introduced its own serious challenges. Nobody had ever built large ocean-going vessels entirely with welded construction at this scale. The technology was relatively new for major shipbuilding. Traditional shipbuilders worried about weld integrity, about stress concentrations at joints where cracks could propagate, about catastrophic structural failures in rough seas. Their concerns weren't merely conservative resistance to change. They were grounded in legitimate engineering uncertainties about a relatively novel fabrication method applied at unprecedented scale. their concerns weren't entirely unfounded. During the war, several Liberty ships would crack in half in cold northern waters, victims of brittle fracture in poorly designed steel, combined with inadequately controlled welding processes. Ships would literally split in two, their hulls fracturing completely. A British metallurgist named Constance Tipper would eventually identify the problem through painstaking investigation. The steel had too high a ductile to brittle transition temperature. In cold water, it became brittle, and continuous welded seams allowed cracks to propagate across entire joints instead of being arrested by the discontinuous nature of riveted seams. The solution required fundamental changes to steel specifications and more rigorous welding controls. Steel needed higher ductility at low temperatures. Welding procedures needed better control of heat input to minimize residual stresses. Inspection protocols needed improvement. But those fixes came later, after painful lessons. In 1941 and 42, Kaiser was proving that welded construction could work at massive scale, and despite some spectacular failures, the vast majority of Liberty ships stayed afloat and served successfully. Each Liberty ship required nearly 50 miles of welding. At the peak of production, Kaiser's yards were executing that work faster than anyone thought possible, and the ships were functioning effectively in the harsh conditions of the North Atlantic convoy routes. By mid-1942, the Richmond yard had reduced construction time from 197 days to 90 days through workflow improvements and learning. Then, 70 days as prefabrication became more sophisticated. Then, 45 days as every process was refined. The established shipbuilding industry watched in disbelief as Kaiser's methods proved not just effective, but superior in speed to traditional approaches. More importantly, they proved scalable in ways that traditional craft-based methods could never match. Kaiser opened additional yards using the lessons learned in Richmond. 3 more facilities in Richmond alone, each designed from the ground up around prefabrication principles. One massive facility in Portland, Oregon, called the Oregon Shipbuilding Corporation, built on 87 acres along the Willamette River. Another at Swan Island in Portland, occupying nearly 400 acres of land that had previously served as Portland's municipal airport. And in early 1942, the crown jewel of Kaiser's empire, the Vancouver shipyard across the Columbia River in Vancouver, Washington. The Vancouver yard was different from the beginning, designed specifically around the prefabrication principles his team had now perfected through building hundreds of Liberty ships. The facility sprawled across 200 acres of river frontage along the Columbia River, with 12 building ways and a 3,000-foot outfitting dock where completed ships could be finished and tested. But the real innovation wasn't the physical plant. It was the supply chain and workflow architecture that supported it. Kaiser established contracts with factories across America to build standardized modules to exact specifications. A factory in Ohio would manufacture engine mounts, building identical units in large batches. A plant in Pennsylvania would fabricate bulkheads, standardized sections that fit any Liberty ship. Facilities in California would produce superstructure sections. Each piece was designed to fit perfectly with every other piece, truly interchangeable and standardized in ways that had never been attempted in shipbuilding before this massive wartime program. These modules arrived at Vancouver by rail on precisely scheduled deliveries. They were unloaded directly onto the building ways using massive overhead cranes, where crews welded them together in predetermined sequences that had been optimized through building hundreds of earlier ships. A Liberty ship wasn't built from the keel up anymore in the traditional sense. It was assembled from prefabricated sections, each weighing as much as 250 tons, lifted into place by massive cranes and welded together by teams working in parallel across multiple stations simultaneously. The workflow optimization was extraordinarily sophisticated. Instead of hundreds of workers crowding together on a single ship, each competing for limited space and access, creating constant conflicts about who could work, where and when, Kaiser's system distributed work across multiple stations simultaneously. Welders in prefabrication shops worked in optimal positions, mostly downhand welding with the workpiece below them, the easiest and fastest welding position that produced the highest quality welds. This was far more efficient and produced better results than the cramped, awkward overhead and vertical positions required when welding inside a nearly complete hull where access was limited. Kaiser also reintroduced competition strategy that had worked so well on dam construction projects. His Richmond and Portland Yard teams raced to beat each other's production records, with public celebrations and bonuses for winning teams. When the Portland, Oregon Shipbuilding Corporation completed the Liberty ship Joseph N. Teal in just 10 days in the fall of 1942, it was front-page news. Richmond responded by building the Robert E. Peary in 4 days, 15.5 hours in November of the same year, a spectacular achievement that made national headlines and Kaiser a household name. These records were publicity stunts to some degree, achieved with extensive pre-assembly, optimal conditions, and dedicated teams working around the clock. The average construction time was far longer, settling around 42 days by late 1943 across all yards. But the records proved Kaiser's central thesis that had been dismissed as impossible just 2 years earlier. With extensive prefabrication and systematic welding, shipbuilding timelines weren't bound by traditional craft-based limitations. It was fundamentally a manufacturing process that could be accelerated through better workflow optimization and standardization, just like any other manufacturing operation. The workforce made it all possible. At the peak of production in late 1942, Kaiser's 3 Northwest yards, Oregon Shipbuilding, Swan Island, and Vancouver employed 97,000 workers, working 3 shifts around the clock. The Vancouver yard alone had 38,000 employees, more than double Vancouver's entire pre-war population of 18,000 residents. The social transformation was staggering. Kaiser recruited aggressively across America. Workers came from the South, fleeing agricultural poverty for high-wage industrial jobs. They came from the Midwest, where manufacturing had been depressed throughout the Depression. They came from the East Coast, attracted by promises of meaningful war work and unprecedented opportunities. The workforce was remarkably diverse for the era. Approximately 30% were women, unprecedented in heavy industrial work. Thousands were African American, increasing Portland's black population from 1,800 before the war to an estimated 15,000 by 1946. Native Americans left reservations for the first time to work in defense industries, seeking economic opportunities and a chance to contribute to the war effort. To house this massive influx, Kaiser built an entire city from scratch. Vanport, constructed on Portland's northern edge between the Vancouver and Portland yards, contained 9,942 housing units, accommodating 42,000 residents. It had schools, shops, childcare facilities, and medical clinics. Kaiser established comprehensive medical services for workers that would eventually evolve into the Kaiser Permanente healthcare system, one of America's first and largest health maintenance organizations. The social changes were profound and lasting, but the technical revolution was what mattered immediately for the war effort. By late 1942, Kaiser's yards were producing Liberty ships at an average rate of 1 every 42 days. With multiple ways in each yard and 7 yards in operation across the West Coast, Kaiser's organization was launching roughly 1 complete ship per day across all facilities combined. The mathematics had fundamentally shifted. German U-boats were still sinking Allied ships at frightening rates, but American production had finally overtaken the loss rate. For every ship sent to the bottom, Kaiser's yards and others using his methods were launching replacement ships faster than submarines could sink them. The tonnage equation had reversed. Victory was now mathematically possible, but Liberty ships were only part of Kaiser's ambition. In late 1942, as German U-boats continued their devastating campaign against Atlantic convoys, Kaiser proposed something even more audacious. Mass-produced aircraft carriers built using the same prefabrication techniques that had revolutionized cargo ship construction. The U.S. Navy rejected the idea immediately and emphatically. Aircraft carriers were the most complex and valuable warships afloat, marvels of engineering that represented the pinnacle of naval construction. The Essex-class fleet carriers under construction were technological masterpieces featuring steam catapults, sophisticated arresting gear for landing aircraft, advanced fire control systems, and extensive armor protection. They required 3 years to build using highly skilled craftsmen in specialized naval yards that had been building warships for generations. The idea that Kaiser, who'd only been building ships for barely 2 years and had no experience with warships, could mass-produce carriers like Liberty ships was not just ambitious, it was absurd. But Kaiser understood something the Navy bureaucracy didn't want to admit, a strategic reality they were too invested in traditional approaches to acknowledge. The Battle of the Atlantic wasn't being lost because Allied ships were technologically inferior to their opponents. It was being lost because German U-boats operated effectively in a mid-Atlantic gap beyond the range of land-based patrol aircraft flying from bases in North America or the United Kingdom. Convoys crossing that gap were defenseless against submarine wolf packs that could attack with impunity, surface at night to recharge batteries, and submerge again before dawn. The obvious solution was carrier-based air cover providing round-the-clock anti-submarine patrols. But fleet carriers were too valuable, too powerful, and too expensive to devote full time to convoy escort duty when they were desperately needed for offensive operations in the Pacific. What the Atlantic needed wasn't fleet carriers capable of projecting power against enemy fleets. It needed small, simple escort carriers that could provide air cover for convoys. These jeep carriers, as they'd become affectionately known, didn't need to be fast or heavily armed or impressively armored. They needed to carry anti-submarine patrol aircraft equipped with depth charges and radar, and they needed to be built quickly enough to deploy in meaningful numbers before the tonnage war was lost. Kaiser proposed building 50 small carriers in less than 2 years, using the same prefabrication methods his yards had perfected on Liberty ships. They'd be based on standard cargo ship hulls, modified with flight decks and hangar spaces. No heavy armor, no high-speed capability, no advanced combat systems, just functional flight decks that could launch and recover anti-submarine aircraft to close the mid-Atlantic gap that was killing Allied shipping. The Navy Bureau of Ships rejected Kaiser's proposal decisively. Escort carriers were already being converted from cargo ship hulls by experienced naval shipyards. Kaiser's services weren't needed. His methods were unproven for complex warships. He should stick to cargo vessels where his unorthodox approaches couldn't endanger American sailors. Kaiser went around the Navy. He went directly to President Roosevelt's advisors, appealing to the commander-in-chief over the heads of the naval bureaucracy. Roosevelt understood the strategic reality that the Navy seemed determined to ignore. British and American cargo ships were being sunk faster than convoys could be effectively protected by the available escort forces. The mid-Atlantic gap was a death zone where submarines operated freely. Small carriers providing round-the-clock air patrol could close that gap, saving thousands of merchant seamen's lives and preserving the tonnage needed to sustain Britain's war effort. If Kaiser could build 50 carriers in 2 years, when the Navy insisted it would take 4 or 5 years using traditional methods, that difference could determine whether Britain survived or starved into surrender before American industrial might could turn the tide. In late 1942, Roosevelt personally ordered the Navy to give Kaiser a contract for 50 escort carriers. The admirals complied because they had no choice when the president issued direct orders, but their skepticism was palpable and openly expressed. These Kaiser Coffins, as some naval officers derisively called them in private conversations, would be lightly built, poorly armed, and dangerously unseaworthy. Kaiser's profit-driven shortcuts were going to get American sailors killed at sea. Kaiser's Vancouver yard began conversion for carrier production in November 1942. The Casablanca-class escort carrier design was relatively simple compared to massive fleet carriers. 511 feet long, displacing 11,000 tons fully loaded with fuel, ammunition, and aircraft. Powered by Uniflow reciprocating engines, the same outdated technology used in Liberty ships that could barely push the ships to 20 knots maximum speed. They would carry 28 aircraft and a crew of 910 officers and enlisted men. The flight deck was unarmored wood planking, vulnerable to any hits. The hull was thin steel, barely adequate for merchant service, let alone combat. The ships rolled dramatically in rough seas, earning a reputation for making even experienced sailors seasick. Everything about them screamed compromise and corner-cutting. Naval architects who'd spent entire careers designing elegant warships looked at Kaiser's carriers with professional horror and saw disasters waiting to happen. But disasters don't care about elegance. They care about what actually works in combat, and Kaiser's supposedly inadequate carriers worked remarkably well. The prefabrication system adapted beautifully to carrier construction. The hull was essentially a modified cargo ship, built using established Liberty ship techniques that were now refined to near perfection. Prefabricated sections arrived by rail from suppliers across America, were lifted into place by massive cranes, and welded together by experienced crews who'd built hundreds of ships. The flight deck was a separate modular structure, manufactured in sections at specialized facilities and installed atop the completed hull. Hangar spaces, crew quarters, and machinery spaces were all prefabricated modules that arrived complete with internal systems already installed. The Vancouver Yard's 12 building ways allowed simultaneous construction of multiple carriers. Work crews moved from station to station, repeating identical tasks on ship after ship after ship. A welder who'd mastered one specific joint type on one carrier could execute that exact joint on every subsequent carrier with increasing speed and precision. Learning curves that took weeks on early ships compressed to days on later vessels. The supply chain was the real innovation underlying everything else. Kaiser's procurement team had mapped every component, identified every potential bottleneck, and established long-term contracts with suppliers who could deliver standardized parts on predictable schedules. Aircraft catapults came from one specialized manufacturer, arresting gear from another dedicated supplier. Triple expansion engines from Joshua Henry Iron Works in Sunnyvale, California, where Kaiser had a major ownership stake ensuring priority delivery. Everything was standardized to unprecedented degrees. Everything was designed to be interchangeable. A bulkhead manufactured for ship number 20 would fit perfectly into ship number 35 without modification. Replacement parts could be manufactured anywhere in America and installed on any Casablanca-class carrier in the fleet without custom fitting. This interchangeability would prove absolutely crucial during the war. When a carrier was damaged in combat, replacement sections could be manufactured at factories in the United States, shipped to forward repair facilities in the Pacific, and installed quickly to restore the ship to service. The ships weren't beautiful, and they weren't sophisticated, but they were eminently maintainable, and in wartime, maintainability matters infinitely more than aesthetics. The first Casablanca-class carrier, originally christened Alazon Bay but later renamed Casablanca after the successful North African battle, was launched on April 5, 1943. Eleanor Roosevelt, the First Lady and one of America's most recognizable public figures, attended the christening ceremony and broke the traditional champagne bottle across the bow. An estimated 75,000 people, one of the largest crowds in Vancouver's history, lined the riverbanks to watch the launch. Kaiser had promised the Navy 16 carriers by 1944 in his original contract proposal. His team, embracing the competitive spirit that drove everything Kaiser did, adopted the slogan, 18 or more by 44, encouraging workers to exceed the contract requirements. Competition between work crews intensified, as each launch was celebrated with publicity, bonuses, and public recognition. Workers who'd been shopkeepers and waitresses just months earlier were now building aircraft carriers at a pace the Navy had declared completely impossible, and they took fierce pride in their achievements. Between April 5, 1943 and May 27, 1944, Kaiser's Vancouver Yard launched 50 complete escort carriers in an astonishing display of industrial capacity. That's nearly one complete aircraft carrier per week, sustained for over 13 months straight. The fastest carrier construction from keel to launch was completed in approximately 3 months, though final fitting out and sea trials added several more weeks before delivery to the Navy for operational deployment. But the Vancouver Yard's most spectacular public relations achievement, the record that made headlines across America and boosted morale at a crucial moment in the war, was the 72-hour vessel. On November 16, 1942, before carrier production had even begun, the Vancouver yard was still primarily building cargo ships and landing craft. The yard superintendent, Clay Bedford, proposed an audacious challenge to demonstrate the absolute limits of prefabricated construction. Using maximum prefabrication, optimal workflow coordination, and perfectly timed deliveries, how fast could they build a small vessel from raw materials to launch-ready, not a full Liberty ship? Those were too large and complex for a pure speed record. But a smaller landing craft or auxiliary vessel, something with all essential components, hull, deck, basic machinery, launching capability that would demonstrate what was theoretically achievable with perfect execution. The yard picked a vessel type that was simple enough to be realistic but complete enough to be meaningful. It would have all essential ship components, real structure, real systems, real capability. This wouldn't be a mock-up or publicity stunt. The clock started. Workers who'd rehearsed their specific tasks repeatedly moved through predetermined sequences with military precision. Prefabricated sections arrived from staging areas at precise intervals, coordinated down to the minute. Welders worked in parallel across multiple stations, each focusing on their specialized joint types. There was no wasted motion, no waiting for materials, no confusion about who did what task next in the sequence. 71 hours and 40 minutes later, the vessel slid into the cold waters of the Columbia River to thunderous cheers from assembled workers and spectators. Not a publicity stunt using completely pre-assembled pieces merely bolted together, but an actual functional ship built from individual plates and modules in less than 3 full days. The record stood as dramatic proof that with sufficient preparation, standardization, and workflow coordination, shipbuilding timelines were limited only by how well you could optimize every single step of the process. The Navy stopped calling Kaiser's carriers coffins after the Battle off Samar. On October 25, 1944, during the larger Battle of Leyte Gulf in the Philippines, a small American task unit designated Taffy 3 found itself unexpectedly facing the full might of the Japanese center force. This wasn't supposed to happen according to any operational plan. Admiral Halsey's powerful Third Fleet, with its fast battleships and fleet carriers, was supposed to be protecting the landing areas at Leyte. But Halsey had pursued a decoy Japanese carrier fleet north, inadvertently leaving Taffy 3 as the only American force between overwhelming Japanese battleship firepower and completely undefended American transports landing troops at Leyte Gulf. Taffy 3 consisted of 6 Casablanca-class escort carriers, 3 destroyers, and 4 destroyer escorts, a force designed for anti-submarine patrol and ground support, not surface combat. They faced 4 Japanese battleships, including the legendary Yamato, the largest battleship ever built with 18-inch guns that could obliterate any escort carrier with a single hit, plus 6 heavy cruisers, 2 light cruisers, and 11 destroyers. The Japanese had overwhelming firepower advantage, 3-to-1 speed advantage, and complete tactical surprise. What followed over the next 2.5 hours was one of the most desperate and heroic naval battles in American history. The escort carriers immediately launched every aircraft they had, despite being equipped primarily for anti-submarine work with depth charges and high-explosive bombs, rather than the armor-piercing weapons needed against battleships. The destroyers and destroyer escorts made suicidal torpedo runs against battleships, charging straight at ships that could sink them with single salvos, buying precious minutes for the carriers to attempt escape, and the supposedly inadequate escort carriers themselves fought back with every weapon available. The USS Street Low and USS Kalinin Bay became the only U.S. aircraft carriers in history to ever record gun hits on enemy warships with their own guns. Street Low's single 5-inch gun struck a Japanese destroyer with a lucky hit. Kalinin Bay's gun crew damaged a heavy cruiser with 2 hits that started fires. USS White Plains may have delivered the fatal blow to the heavy cruiser Chokai, landing 6 5-inch shells at near maximum range that triggered a massive secondary explosion, probably detonating the cruiser's own torpedoes, that proved fatal. The Japanese, confused by the ferocity of the American defense and increasingly concerned about potential additional American forces approaching, made the shocking decision to withdraw despite their overwhelming advantage. Taffy 3 had held the line against impossible odds. The landing at Leyte proceeded safely. American soldiers got ashore, but the cost was severe and heartbreaking. The USS Street, Lowe, was sunk by a kamikaze attack later that day, the first major warship sunk by organized kamikaze assault. The USS Gambier Bay was sunk by Japanese gunfire during the battle. Over 1,000 American sailors died in the cold Pacific waters, but Kaiser's supposedly unseaworthy carriers had fought the largest battleship ever built and survived. They'd proven they could take tremendous punishment, absorb damage, and keep functioning. They demonstrated that simplicity and numbers could overcome sophistication when used with courage. The derisive term Kaiser Coffin disappeared from official naval correspondence after Samar. Those who'd survived the battle spoke of the little carriers with respect and gratitude. By war's end in August 1945, Kaiser's Vancouver yard had completed. All 50 contracted Casablanca-class carriers, exactly on the accelerated schedule Kaiser had promised. At least 15 were damaged or sunk in Pacific combat operations, testament to how heavily and aggressively they were employed in dangerous situations. The surviving carriers served through the war's end and beyond, providing air cover for amphibious landings across the Pacific, hunting submarines in both oceans, conducting ground support missions their original designers never anticipated, and proving their worth in ways that silenced even their harshest early critics. Kaiser's total wartime production across all 7 yards was staggering even by the standards of America's massive industrial mobilization. His yards built 1,490 ships, representing 27% of all vessels ordered by the U.S. Maritime Commission during the entire war. This included 821 Liberty ships, 219 improved Victory ships, 50 Casablanca-class escort carriers, and numerous landing craft, tankers, troop transports, and auxiliary vessels. The human and social impact was equally profound and lasting. Kaiser's aggressive recruitment policies and relatively equitable hiring practices brought unprecedented diversity to shipyard work and demonstrated possibilities for post-war America. Women comprised up to 30% of the workforce at peak employment, working as welders, crane operators, and supervisors in jobs previously closed to them. African American workers filled skilled positions that had been systematically denied to them in pre-war industry, proving their capabilities and demanding recognition. The experience of working together in integrated crews, while far from perfect and still marked by discrimination, provided a glimpse of what a more equitable post-war America could become. Kaiser's medical program, pioneered by Dr. Sidney Garfield, established comprehensive prepaid health insurance for workers and their families. The system provided quality care efficiently and affordably, demonstrating conclusively that healthcare could be effectively organized as a benefit of employment rather than charity or private fee-for-service medicine. After the war, Kaiser privatized these medical facilities as Kaiser Permanente, which grew into one of America's largest health maintenance organizations, serving millions of members. Vanport, the worker city Kaiser built to house shipyard employees, met a tragic and devastating end. In May 1948, a Columbia River dike failed during seasonal flooding, and the entire community was destroyed in a matter of minutes as water swept through. But while it existed, Vanport demonstrated that with sufficient urgency, resources, and determination, entire functional communities with housing, schools, and services could be planned and built rapidly to meet emergency needs. The technical legacy was even more significant and lasting than the social changes. Kaiser's prefabrication methods became standard practice in shipbuilding worldwide. The fundamental concept of building ships from standardized interchangeable modules revolutionized naval architecture. Modern shipyards from Korea to Europe use computerized versions of Kaiser's basic techniques, with modules built in climate-controlled facilities and assembled using advanced automated welding systems. The interchangeability principle influenced manufacturing far beyond shipbuilding. If massive ships could be built from standardized parts assembled rapidly, the same principles could apply to aircraft, vehicles, electronics, and eventually computers. The post-war American economy's manufacturing dominance owed significant debt to organizational and technical lessons learned, building Liberty ships under impossible time pressure. Welding technology advanced dramatically during the war, driven by Kaiser's massive-scale application that exposed problems and drove solutions. Metallurgists learned to control heat-affected zones to minimize brittleness. Engineers developed techniques to prevent crack propagation. Inspectors pioneered non-destructive testing methods to verify weld integrity without cutting ships apart. These advances carried over immediately to petrochemical facilities, pressure vessels, pipelines, and eventually nuclear reactors, where weld integrity is absolutely critical to safety. Kaiser's competitive incentive programs profoundly influenced post-war industrial relations and management philosophy. The concept of rewarding teams for exceeding production targets became standard in American manufacturing. Quality circles, continuous improvement processes, and structured employee involvement programs all trace conceptual roots to Kaiser's shipyard competitions that motivated workers through recognition and friendly rivalry. The workforce training model was equally influential in reshaping how America approached skills development. Kaiser proved definitively that complex technical skills could be taught quickly to motivated learners, given proper instruction, clear procedures, and hands-on practice. This challenged the guild-like apprenticeship systems that had dominated skilled trades for centuries. After the war, vocational training programs adopted Kaiser's accelerated curriculum models, dramatically expanding access to skilled employment. Most fundamentally, Kaiser demonstrated that American industry could adapt to wartime demands far faster than conventional wisdom suggested possible. In 1940, shipbuilding was a craft-based industry, operating on timelines measured in months or years, controlled by established yards with decades of experience. By 1945, it was a mass-production industry operating on timelines measured in weeks, accessible to newcomers willing to challenge assumptions. That transformation didn't happen because of direct German or Japanese military pressure forcing innovation. It happened because an outsider who didn't know shipbuilding was impossible approached the problem fresh, without preconceptions about how things had to be done, and applied principles from dam construction to an entirely different industry. Henry Kaiser died in August 1967 at age 85, more than 2 decades after his shipyards closed and his workforce dispersed. By then, his Liberty ships had been scrapped for steel or sold to foreign operators. His escort carriers were long gone, victims of post-war drawdowns that sent most to scrapyards. Vanport was a fading memory. But the systems and methods he pioneered had become so thoroughly integrated into American manufacturing that their origins were largely forgotten. Modern naval architects designing prefabricated modules for modular construction don't necessarily know they're using Kaiser's methods refined over decades. Engineers specifying welded construction over riveting don't consciously think about 1942. Workers receiving rapid skills training don't realize they're benefiting from wartime innovations developed under desperate pressure. The techniques have become invisible through ubiquity. That might be the truest measure of Kaiser's lasting success. His revolutionary methods became invisible not because they failed or were abandoned, but because they worked so extraordinarily well they became standard practice, invisible precisely because they're now universal and taken for granted. The 72-hour ship was never meant to be practical or replicable for routine production. It was meant to be possible. It demonstrated conclusively that with sufficient preparation, standardization, and coordinated effort executed with precision, the supposedly impossible became merely difficult. And the difficult became routine when repeated hundreds of times with continuous improvement. That was Kaiser's fundamental gift to America's war effort. Not faster ships, though that's what he delivered. Not better organization, though that's what he implemented. His real contribution was demonstrating that limits exist primarily to be tested, that conventional wisdom deserves healthy skepticism, and that sometimes the only qualification needed to solve an intractable problem is the audacity to believe it can be solved differently. In 1940, the British needed 60 cargo ships, desperately. The established shipbuilding industry confidently said it would take years using proven traditional methods. Kaiser built thousands of ships in the time the acknowledged experts said couldn't be done. He accomplished this by systematically ignoring centuries of accumulated tradition and asking a fundamentally simpler question that cut through complexity. How fast can materials be assembled if nothing unnecessary gets in the way? The answer was 72 hours for a small vessel under optimal conditions, 42 days average for a Liberty ship in routine production, 3 months for an aircraft carrier from keel to launch, and the accumulated answer, over 4 years of sustained war production, was fast enough to carry 2 million American soldiers across the Atlantic and Pacific Oceans, fast enough to deliver the ammunition and fuel and food that kept those soldiers fighting effectively, fast enough to turn raw industrial capacity into decisive military victory. The welder mentioned in the title wasn't one person performing miracles. It was thousands of people, most of them women, many of them minorities, virtually all of them trained in weeks to execute complex skills that traditional craftsmen insisted required years of apprenticeship to learn properly. They were waitresses and farmers and shopkeepers who became welders, because Kaiser believed welding was fundamentally a learnable skill, not a mystical craft requiring innate talent. Because he believed training was simply a process that could be optimized and accelerated like any other process. The destroyer that launched every 72 hours wasn't actually a destroyer in naval terminology. It was a proof of concept, a demonstration that shipbuilding was fundamentally manufacturing, and manufacturing was about workflow optimization, not tradition or mystique. The real warships, the escort carriers and landing craft and troop transports, took longer to build, but not much longer. And in wartime, saving weeks or months is often the difference between victory and defeat, between soldiers supplied or starving, between missions accomplished or abandoned. The British delegation that arrived in America in 1940, desperately asking for 60 ships, couldn't have imagined that American yards would build over 5,000 vessels. The Navy admirals who rejected Kaiser's carrier proposal as impractical couldn't have imagined that his yards would build 50 combat-effective carriers in the time frame they declared impossible. The traditional shipbuilders who insisted prefabrication fundamentally wouldn't work couldn't have imagined that their centuries-old methods would become essentially obsolete within 5 years. They couldn't imagine these outcomes because they knew too much about how things had always been done, how ships had always been built, what the limitations supposedly were. Kaiser's strategic advantage was productive ignorance. He didn't know shipbuilding was supposed to be slow, so he made it fast. He didn't know carriers were supposed to take years, so he built them in months. He didn't know welders needed years of training, so he trained them in weeks. And because he didn't know these things were impossible, he did them anyway. That ignorance, combined with rigorous attention to workflow optimization, continuous improvement, and systematic coordination, changed naval warfare fundamentally. It changed American manufacturing permanently. It changed what entire industries considered possible or achievable. And it demonstrated that sometimes the most valuable thing an expert can do is get out of the way and let someone who doesn't know the rules rewrite them entirely. And it all started with a man standing in a mudflat in Richmond, California, in 1940, looking at a shipyard that didn't exist yet, envisioning production lines that hadn't been designed, imagining workers who hadn't been hired, and asking the simplest possible question that cut through all complexity. How fast can we build ships if we completely stop building them the way ships have always been built? The answer reshaped the world and won a war. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.